Hello and welcome back. We're going to continue looking at section 11.2 today, inference for relationships. So, last time we looked at how to find expected counts in this situation. We found all 9 of these using this formula basically here, as you can do the row total times the column total divided by the table total. So next thing we're going to talk about is the conditions that need to be met in order to calculate the chi-squared statistic. So these are going to look pretty similar. All expected counts are at least 5, so that satisfies the large sample size condition. Then the random condition is met because in the initial explanation of this problem, the treatments were assigned at random 2 different times. And then for the independent condition, we've got some concerns here. So basically, to meet the independent condition, all 3 groups should be independent of each other, which is true because it's a randomized experiment, so the 3 groups are independent. That's the first thing. But also individual observations, that it would be individual bottles of wine sold, also should be independent. But if you think about this situation, that might not be true, because if a customer buys more than 1 bottle of wine at the same time, if I know that their first bottle of wine is a French wine, that might give us additional information about the other bottles bought by this customer, because they might have tendencies to buy a particular type of wine. Now, if that were the case, the independent condition would be violated. However, if each customer only buys 1 bottle of wine, then this condition is probably met. Since we can't be sure what was actually happening, we'll proceed with caution. Now, just as we did with the goodness of fit, we compare the observed counts to the expected counts using the same formula. This time the sum is over all the cells, not including the totals in the two-way table. So here are the observed counts, here were the expected counts. Notice all the totals are the same. That should always happen. And then I compare basically this observed count with this expected count. So I do this observed count, 30 minus 34.22 squared divided by the expected count, 34.22, I get 0.52. Then I do that for every cell. So I do that 8 more times, and I add up all those results, and I get about 18.28. And that number is my chi-squared statistic. Now, what do I do with that? Well, when my conditions are met, I perform a test where the null hypothesis is there is no difference in the distribution of the categorical variable for several treatments in this case. And then I use a chi-square distribution with these degrees of freedom. So it's number of rows minus 1 multiplied by the number of columns minus 1. And this new procedure is called a chi-square test for homogeneity. And then I find the area to the right of that chi-squared statistic in the chi-squared distribution with that many degrees of freedom. So for this example, we set our null hypothesis is there's no difference in the distribution of wine for my 3 different treatments of no music, French accordion music, and Italian string music. And my alternative is that there is a difference in the distribution of wine purchases at the store for no music, French music, and Italian music. So we decided to proceed with caution because of the independent condition. And then our calculated statistic was 18.28. If you use table C, you would go to row 4, and you would find that 18.28 is between these 2 values, so our p-value is between these 2 values. Or if you go to your calculator, you would go distribution, and we would go to a chi-squared CDF, and we want to find the area to the right of the lower bound is 18.28. Upper bound is very large number and degrees of freedom. The number of rows is 3 minus 1 times 3 minus 1. So our degrees of freedom is 2 times 2, which is 4. And then we find our p-value of 0.001. So such a small p-value does give us convincing evidence to reject the null hypothesis, and we are able to conclude the alternative. So we conclude that there is a difference in the distributions of wine purchases at this store. Furthermore, the random assignment allows us then to make basically a cause and effect conclusion and say that this difference in distributions is actually created by the music that is being played. So putting all those steps together, this is called a chi-squared test for homogeneity. So when our three conditions are met, a chi-squared test for homogeneity uses this null and alternative hypothesis. We start by finding expected counts, calculate this chi-squared statistic using this formula, where we sum over all the cells in the two-way table. And then if the null hypothesis is true, the chi-squared statistic has an approximate chi-squared distribution with degrees of freedom that's equal to number of rows minus 1 multiplied by the number of columns minus 1. Then the p-value is the area to the right of the chi-squared statistic under that density curve. And of course, there is a way to do this on our calculators. So the way we type in a two-way table in our calculator, because this time it's not a list, it's actually like we want like 3 lists. So we're actually going to use the matrix menu for this test. So I go second, and then matrix is right there. And then I'm going to go and edit matrix A. So I go over to edit, I select matrix A, and I want this to be a 3 by 3 matrix. So 3 rows and 3 columns. And then I type in all my observed counts, just like they were in this original table right here. I type in these 9 numbers in the exact same way they are in that table. Now, here's the thing about this test is I do not need to type in the expected counts. At this point, I can just go to stat and test, and then I can go to chi-squared test, not chi-squared GOF, chi-squared test, option C. And then my observed numbers I put into matrix A, and this is where my calculator will actually place all the expected counts for me. So I can choose any matrix I want. I'm going to place it in matrix B. The way I type matrix B is go back to the matrix menu, and from this screen you can select which matrix you want to type. And then I hit calculate. And you'll notice there's the chi-squared statistic and there's the p-value that I found with that many degrees of freedom. And then you'll also notice if I now go back to my matrix menu, I actually have numbers in matrix B now. So on my main screen, I can type matrix B, press enter, and that's how I can find the expected values that my calculator finds when it does the test. All right, so expected values, we talked about that. So let's look at another example here. So random digit dialing telephone surveys used to exclude cell phone numbers, which was a problem. But it really was only a problem if the opinions of those who had cell phones were different than those who had regular wired landlines in their homes. So the Pew Research Center interviewed separate random samples of cell phone only and landline telephone users who were less than 30 years old, and here's what they found about how they described their political party affiliation. So you can see here, one of the key differences I see between these two groups is a much larger green area for this group compared to this group, and a slightly larger blue area and even a slightly larger red area for this group compared to this group. So I'm going to perform a test to see if these two distributions could actually be the same or not, or come from the same population, I should say. So basically, my null hypothesis is that there's no difference in the distribution of party affiliation for these two groups, the cell-only and the landline populations. The alternative is that there is a difference, and I'm going to use significance level of 0.05. So that's the state. Plan, I'm going to use a chi-squared test for homogeneity if conditions are met. And my conditions are random, and it does say that there were 2 separate random samples here of the 2 different groups. There is no normal condition, or there's the large sample size condition. So I want all expected counts to be at least 5. The problem is that these aren't the expected counts. What I'm actually going to do is use my calculator to find the expected counts right now. So even though I haven't really approved running of the test yet, because I haven't checked all the conditions, I'm going to run it anyways. So I go to matrix, I type in my observed counts into matrix C, which I've already done. You can see those, I've already put those values in there, except I accidentally included a row for totals. I need to get rid of that. So I'm going to go second matrix, I go to edit, I'm going to type this as matrix C, and I actually want a 3 rows and 2 columns, and there are the 6 observed counts I got for those 6 categories. All right, now I'm ready to go to stat and test, and then it's going to be towards the bottom of my list. Option C is a chi-squared test, and my observed counts are in matrix C this time, and I'm going to have it put my expected counts into matrix. Let's go to this first blank one here, matrix D. And now this is how I can get these values, which I'll come back to later. What I really wanted right now is the expected counts. So I'm going to go to matrix D, press enter, and then press enter again to review the entries, and those are the 6 expected counts. So I write those down and I indicate that I know that they are all at least 5, and so this condition is met. Then the independent condition. So again, I need to state that there are 2 independent groups, the 2 samples of 2 independent groups. And then I also need to check that individual observations are independent. And because we're sampling without replacement, I check the 10% condition for each group. So yes, it's reasonable to assume there are at least 960 cell users under 30 and at least 1,040 landline users under 30. There's a lot of people in the US, so yes, that's safe to assume. Since conditions are met, I can now calculate the test statistic and the p-value, which I already did on my calculator. So there's my test statistic and then p-value. Now notice this p-value is quite a bit larger than 0.05. So because of that, we fail to reject the null hypothesis, and we do not have enough evidence to conclude that the distribution of party affiliation differs. Does that mean that I'm saying there is no difference between the 2 groups? No, I just don't have enough evidence to say there is. So if I truly still think there is a difference between these groups, I should basically try this whole thing again, but with bigger samples, because I might be trying to detect a pretty small difference between these 2 groups. All right. And finally, a follow-up analysis. So just like with the goodness of fit test, if we do get a reject of the null hypothesis, we often will want to do a follow-up analysis that examines those differences in detail. Basically, we look at which cells have the biggest deviations between the observed and expected, and we look at individual components. So to get the components, we would use some statistical software, and sometimes on tests, something like this is printed for you. So here's the output table for that wine, music, and types of wine sold. So you can see that the biggest contributions here are right here and right here are the biggest contributions. So that's the third number in each one of these. So you can see that that 7 point something and 6 point something, that accounts for a lot of that 18, because you get that from adding up these 9 numbers there on the bottom of each one of those. So those 2 areas account for a lot of the chi-squared statistics. So that tells us that, during French music, I think this was Italian wine, we sold way less than expected. And here, when Italian music is played, Italian wine was sold way more than expected. So that leads us to a conclusion that the sales of Italian wine are strongly affected by Italian music and French music. Italian music causes us to sell more than expected, while French music causes us to sell less than expected. So just to review here, we've looked at, back in chapter 10, how to compare 2 proportions. So if you're only comparing 2 groups, you would use those skills from chapter 10. And now the chi-square test for homogeneity allows us to compare several proportions, so like more than 2, to each other. And then, just like last time, be careful with your alternative hypothesis. Don't state it as they are all different, because some of them could be the same. So think about it this way. The opposite of all proportions are equal is that some of the proportions are not equal. So that's it for today. Please send me any questions.